In this video, we discuss the properties of cyclic groups and some examples related to cyclic groups will be discussed. And the cyclic groups are broadly from group theory, and that is from the section Algebra. And I will show you one question that has come in TS set 2019 and 3 questions. That's what I have prepared for you that will be discussed. And this lecture is suitable for JL, DL, AP set, IIT JOM, J8 and CSIR NET examinations also. So first we talk about the properties of cyclic groups. Our first concern is, what is a cyclic group? A group G is a cyclic group if there is an element A belongs to G such that every element of G is of the form A power I, where I belongs to Z. That is, if there is an element A belongs to G such that G is equal to the set of all A power I belongs to the set of integers. That is our definition of cyclic group, and the properties we have learned in our BSc and MSc classes. The first property is, every group of prime order is cyclic. Every group of prime order. If the order of the group is a prime number, then it is cyclic. Every cyclic group is an abelian group. So every cyclic group is abelian. What about the converse of it? But not conversely. That is the converse of this. That means there are examples of abelian groups which are not cyclic. What are the counter examples? K4. The Klein's 4 group is abelian, but it is not cyclic. And Q plus, set of rational numbers under addition, is an abelian group, but there is no element which will generate every element of Q. Therefore, it's not cyclic. Agreed. And a finite group G of order n is cyclic if G contains an element of order n. If you have a finite cyclic group of order n, G, let us say, then G will have an element of order n, and that is the generator of that element. If G is a cyclic group of order n generated by an element A, then A power k is a generator of G if and only if the GCD of k, n is 1. So you have a cyclic group G of order n and generated by A. Then A power k is a generator of G, is also a generator of G if and only if the GCD of k with n is 1. Agreed. Every subgroup of a cyclic group is cyclic, but a group G need not be cyclic if every subgroup of G is cyclic. So you have a group G. Every subgroup of G is cyclic. Now, is that G necessarily be cyclic? No, not necessarily. What are the counter examples? The counter examples are K4 again. So in K4, every subgroup of G, every subgroup of K4 is cyclic, but K4 is not cyclic. Q8, Quaternion group. In that, every subgroup is cyclic, but it is not cyclic. So Q8 is not generated by a single element. So counter examples are very important for all the competitive examinations, like set examinations and CSIR NET examinations and so on and so forth. If G is a cyclic group of order n and D is a divisor of n, it's a very important property, then the number of elements of order D in G is phi of D. So you have a cyclic group of order n and D is a positive divisor of n, D divides n, then the number of elements of order D in G is phi of D, where phi is the Euler's phi function, and it is a very important property. Agreed. Now we go for an example. Still some more properties are there that I will tell you after example 1. Consider the following two statements. Statement A: the complete list of elements of order 20 in Z800 under addition modulo 800 is these elements: 40, 120, 280, 360, 440, 520, 680, 760. We are talking about list of all, complete list. Complete list means list of all elements of order 20 in this group Z800 under addition modulo 800. All those elements are these. Right. And the statement B is the group G is cyclic. What is G? Where G is the set of all those 3 by 3 matrices whose first row is 1 AB, 0 1 0, 0 0 1, where AB belongs to the finite field of 5 elements. AB belongs to Z5 because 5 is prime, Z5 is a field. So AB belongs to ZB under matrix multiplication. Now the question is, this one is a group. Is it cyclic? That's the question. And we are given the options. The routine options are there. Which of them is true, which of them is false, and so on and so forth. So let's now work out these two problems with the properties that we know. Right. We talk about statement A. So we have a cyclic group Z800, under addition modulo 800. And we want to find the complete list of elements of order 20, and these are given to us. Is it true? That is the question. Now, solution. We have the cyclic group. Zn is always cyclic. Zn under addition modulo n is always cyclic. For n is equal to 800, it's also cyclic group. Now, the number of elements of order 20 in Z800, the number of elements of order D in Zn will be phi of D. So here is order 20, this is phi of 20. Phi of 20 is phi of prime factorization is 2 square into 5. So phi of 2 square into 5 is 2 square into 5 into 1 minus 1 by 2 into 1 minus 1 by 5. So simplifying, you will get 8. Phi of 20 is 8. So we start with an element A of Z800 of order 20. So getting to Z800, and what is that least element whose order is 20? Obviously it is 40. 40 into 20. So that will let A is equal to 40. Then order of A is 20. Agreed. Now consider H, the cyclic subgroup generated by A. Then now A is 40. The cyclic subgroup generated by A will be 0, the additive identity. A, 2A, 3A, 4A, 5A, etc. 19A. These are the 20 elements. Order of H is 20. Agreed. Note that every generator of H is of order 20. Yeah, because every generator is a cyclic group. Every generator of this is 20. And we know A power k is a generator of G if and only if the GCD of k comma n is 1. But it is under multiplication notation. But here you have addition modulo 800. So under addition, A power k will be Ka. So k times A is a generator of G if generator of H if and only if the k comma n is 1. So they are given by Ka, where k comma order of H is 1. That is k comma order of H is 20 is 1. So what are those k? such that they are relatively prime to 20. So k is equal to 1, 2 is not, 3 yes, 4 is not, 5 is not, 6 is not, 7, 9, 11, 13, 17, 19, etc. You verify. So these are the k's. So that means for each k, ka will have order 20 because that is a generator. That is a generator. Therefore, the elements of order 20 are A, 3a, 7a, 9a, 11a, 13a, 17a, 19a. So what are they? What are they? That is, A is 40, 3a is 120, 7a is 280, 9a is 940s are 360, 440, 520, 680, 760. So these are all the elements of order 20. So therefore, the statement A is true. The statement A is true. So let's move to the statement B. In this statement B, the group G is cyclic, where G is the set of all those 3 by 3 matrices 1, A, B, 0, 1, 0, 0, 0, 1. AB belongs to a finite field of 5 elements. And this is a group under matrix multiplication. Right. Now first note that G is an abelian group of order 25, since AB belongs to Z5. Now you see, note that what is G? G is a subset of SL35. What is SL35? Special linear group of all 3 by 3 matrices with entries coming from 5. So all what kind of 3 by 3 matrices? Of determinant 1. So this is of determinant 1. So every matrix of G is of determinant 1. Therefore, G is a subset of SL35. The order of SL35 is finite, and if G is just closed under multiplication, that is sufficient. So you take X, you take Y and multiply, then you will get this one. And it's a gain of the element that belongs to G. So therefore, it is a group. And further, xy is equal to yx because a plus c is equal to c plus a, b plus d is equal to d plus b in Z5. So xy is equal to yx. Thus, G is an abelian group of order 25. How? A takes the values, 5 values, 0, 1, 2, 3, 4, 5. B takes 5 values, 0, 1, 2, 3, 4, 5. Therefore, the number of elements in G will be 5 into 5. That will be 25 elements will be there. Thus, G is an abelian group of order 25. Agreed. Now, let us take an arbitrary element x in G. Then, now look at the square of it. It is 1, 2a, 2b, 0, 1, 0, 0, 0, 1. X cube, 1, 3a, 3b, 0, 1, 0, 0, 0, 1. X4, 1, 4a, 4b, 0, 1, 0, 0, 0, 1. X power 5, 1, 5a, 5a, 5b, 0, 1, 0, 0, 0, 1. But in Z5, 5 is 0. 5 is 0. So, because it is Z5 is a field of characteristic 5. So, characteristic prime number P. So, that is 1, 0, 0, 0, 1, 0, 0, 0, 1. That is identity. And 5 is the least positive integer such that x power 5 is identity. Therefore, the order of x is 5. X is arbitrary. Therefore, each element of G is of order 5. So, each element is of order 5. We do not find any element of G whose order is 25. Therefore, G is not cyclic. So, therefore, the group G is not cyclic since G has no element of order 25 because every element of G is of order 5. Therefore, G is not cyclic. So, this will tell you the statement B is not true. So, thus we have proved statement A is true, statement B is false. And let's look at our option. Option 1 says statement A is true, statement B is false. Therefore, the answer to this question is option 1. That is the detailed discussion of the given question, the problem, the example 1. That's what we have prepared for you. Now, let's now move further for the further properties. Some more properties of cyclic groups. So, a cyclic group with only one generator can have at most 2 elements. What is that cyclic group with only one generator? It is 1 comma minus 1 under multiplication. What are the generators? Minus 1. Minus 1, and minus 1 is the only generator for that. And it has 2 elements. So this statement says a cyclic group with only one generator can have at most 2 elements. If G is a cyclic group of order n, then the number of generators of G is phi of n. It's a very well known result, and problems related to this property, there are several problems that has come in AP set examination, and there are one or two properties that I have seen in the CSIR net examination also, but I have not made any question on that because it is very simple. So anyway, an infinite cyclic group has precisely 2 generators. So for example, Z plus is an infinite cyclic group, and which has only 2 generators. What are the 2 generators? 1 and minus 1 are the only 2 generators. And now if G is an infinite cyclic group, then G is isomorphic to Z plus. Any infinite cyclic group is isomorphic to Z plus. And if G is a finite cyclic group of order n, then G is isomorphic to Z by nz, namely Zn. So if G is a finite cyclic group of order n, then G is isomorphic to Zn. So these are the 2 characterizations of cyclic groups. And any 2 finite cyclic groups of the same order are isomorphic. It's very simple. So the order of a cyclic group and the order of its generators are same. They are equal. Let G be a group of order P into Q, where P and Q are prime numbers, P less than Q. Then the property 1 says G has a subgroup of order P and a subgroup of order Q. Further, if P does not divide Q minus 1, then G is cyclic. This is a very important property, and somebody can exploit this property in the form of a question also. Now, let us now go to a question. This is an example 2. That's what we have created for you. The number of cyclic subgroups of the group U30, U of 30, the units of Z30, is, we are given 4 options. Right. Now, solution. U30 is the set of all those natural numbers n belongs to n, such that n is less than 30, and the GCD of n with 30 is 1. And what will be the order? The order of U30 will be phi of 30, because all those which are relatively prime to 30, how many will be there? Phi of 30. What is phi of 30? Phi of 2 into 3 into 5, and they are relatively prime. 2 and 3 are prime, 3 and 5 are relatively prime. So a pairwise prime. So that it will be phi of 2 into phi of 3 into phi of 5. Phi of 2 is 2 minus 1, phi of 3 is 3 minus 1, phi of 5 is 5 minus 1. Compute it, you get 8. So U of 30 is, what are all those numbers n less than 30 which are relatively prime to 30? 1 is prime to 30. 2, no. 3, no. 4, no. 5, no. 6, no. 7, yes. 7, the greatest common divisor between 7 and 30 is 1, 7. In a similar manner, 11, 13, 17, 19, 23, 29. And it is an abelian group because these are numbers and commutativity is there. It's a group. UN is a group under multiplication. And it is an abelian group of order 8 under multiplication. Right. So what is the question? The question is, how many cyclic subgroups are there for this? So now note that you take the identity element and the subgroup generated by 1 is 1 only. Set 1 is a cyclic subgroup. And in the next element 7 I take. The cyclic subgroup generated by 7 is 7. 7 sevens are 49. Modulo 30 is 19. 19 into 7. Modulo 30 is 13. 13 into 7, 91. Modulo 30 is 1. And here it is also generated by 13. It is also generated by 13. And if you take 19, 19 generates a cyclic subgroup of order 2, that is 19 and 1. That I will talk about that later. After 7, we go to 11. So cyclic subgroup generated by 11. 11 square 11. 11 square is 121, modulo 30 is 1. So it's a cyclic subgroup of order 2. After 13, after 11, 13. The cyclic subgroup generated by 7 is same as cyclic subgroup generated by 13. The next is 17. And it is 17, 19, 23, 1. And it is also generated by 23. Right. After 17, 19. It is a cyclic subgroup generated by 19. And after that 23, the cyclic subgroup generated by 23 is same as cyclic subgroup generated by 17. So we are left with 29. This cyclic subgroup generated by 29 is 29, 1. So we have taken care of all the elements. And the cyclic subgroup generated by them. How many cyclic subgroups are there? There are 6. The number of cyclic subgroups of the group U30 is 6. 1, 2, 3, 4, 5, 6. So where is the answer 6? Option 4. So our answer is option 4. That is the detailed discussion of that question. We move to the next installment of the properties, and that is the last installment. Properties of cyclic groups continued. Now let G be a cyclic group with generator A of order n, and if m less than n, what is the order of A power m? The order of A power m is given by n, the order of A, by the GCD of m comma n. That is the order of the element A power m. You have to remember this, and it is very important. Let A and B be cyclic groups of order m and n respectively. Then A cross B, the direct product, is a cyclic group of order mn if and only if it will become a cyclic group, if and only if the GCD of m and n is 1. It's very important. It is very, very important. And now Zm is a cyclic group of order m. Zn is a cyclic group of order n. Zm cross Zn will be isomorphic to Zmn, provided if and only if the GCD of m and n is 1. It follows from the above. Agreed. It's very important. This is also very important. Let G be a cyclic group of order n. This next property, this is also a good property. For each positive divisor D of n, the group G has exactly one subgroup of order D, that is the cyclic subgroup generated by A power n by D. For each positive divisor D of n, this group G, this cyclic group G of order n, has exactly one subgroup of order D, namely A power n by D. So the number of subgroups of a cyclic group of order n will be the number of divisors of n. From number theory, it is denoted by tau of n. And I will show you a formula for tau of n. If the prime factorization of n is p1 to the power of a into p2 to the power of b into p3 to the power of c, where p1, p2, p3 are distinct primes, then tau of n is a plus 1, the power plus 1 into b plus 1 into c plus 1. As an example, I have taken 3 distinct primes. If you have 4 distinct primes, correspondingly, you have to write the corresponding result. So this is a very important question, and we will go to a question, and that has come in the TS set 2019. It is about the number of subgroups. This question bears a number 68, and the question ID is this one. The given question is the number of subgroups of Z by 9Z, that is the quotient group, cross Z by 4Z other than the trivial subgroup and the whole group itself is. We are given 4 options. Now let's discuss the solution of the problem in detail. Z by nz is isomorphic to Z9. Z by 4z is isomorphic to Z4. So Z by 9z cross Z by 4z is isomorphic to Z9 cross Z4. Now, how 9 and 4 are there? 9 and 4 are relatively prime. So it's isomorphic to Z36. Zm cross Zn is isomorphic to Zmn if m comma n are relatively prime. So 9 comma 4 is relatively prime. Therefore, it is isomorphic to Z36. Z36 is a cyclic group. Zn is always a cyclic group. So therefore, Z36 is a cyclic group of order 36, and the 36, the prime factorization is 2 square into 3 square. The number of subgroups of Z by 9Z cross Z by 4Z is equal to the number of subgroups of Z36. The number of subgroups of Z36 is given by tau of 36. That is equal to tau of 2 square into 3 square. Then it will be 2 plus 1, A plus 1 into B plus 1. That is 2 plus 1 into 2 plus 1. That is 3 into 3, 9. So where is our answer? It is against option 4. Therefore, the number of subgroups other than, the number of subgroups other than trivial subgroup. How many trivial subgroup means? The identity element alone, that is 1. And the group itself, that is also another 1. So other than those 2 elements, that means out of 9, trivial is 1 and the whole group is 1. So 9 minus 2, that is 7. So the answer is option 3, not option 4. Option 4 will give you the total number of subgroups. But the question is the number of subgroups of this one other than trivial subgroup, the identity element alone, and the group itself. So out of the 9, you have to subtract 2. So number of subgroups other than trivial subgroup and the group itself is 7. So to deceive you, the order 9 is also given. So the answer to this question is option 3. That is the detailed discussion of this question. Let's move to the next example. That is the example 3, and this is the last example in this video, and it is again about the number of subgroups. Suppose A is a generator of the group Z25. Z25 is a cyclic group of order 24. Z24. Find the number of subgroups of the subgroup generated by A power 21 intersection the cyclic subgroup generated by A power 10. So, how many number of subgroups will be there for this intersection? That's the question. We are given 4 options. Now, solution. Given Z24 is a cyclic group and it is generated by A. Therefore, the order of A, because A is a generator, order of A is 24. Now, what will be order of A power 21? You know, A power K is a generator if and only if order of A power K will be n by the GCD of n comma K. So n means 24 by GCD of n 24 comma K. K comma n or whatever it is. It is 24 by GCD of 24 and 21 is 3, that is 8. Is an 8 order element. 8 order element. Now get into Z24. Who is that element which is of order 8? It is a power a cube. It's a cube. So therefore, order of a power 21 is equal to order of a cube. I can write. How do I write that a cube? A power 24 by 8, that is 3, a cube. So that way I got this cyclic subgroup generated by this is A3. I have reduced it to lower indices, lower powers. Right. What about the next one? Order of a power 10 is equal to 24 by GCD of 24 comma 10. That is 24 by 2, that is 12. So what is that element A, element of G, whose order is 12, the lowest powers? A square, a power 24 by 12, and that is a power 10 is equal to a power 12 by 24 by 12, that is a square. Now we go for the intersection. A power 21 the cyclic subgroup generated by a power 21 intersection the cyclic subgroup generated by a power 10 is equal to the cyclic subgroup generated by a cube intersection the cyclic subgroup generated by a square. Now you can physically take the intersection and say the answer also. I will show you how you can do without using any formula. So the cyclic subgroup generated by a cube intersection cyclic subgroup generated by a square. The cyclic subgroup generated by a cube is a cube, a power 6, a power 9, a power 12, a power 15, a power 18, a power 21, a power 24 is equal to identity. Intersection. The cyclic subgroup generated by a square is a square, a power 4, a power 6, etc., etc. A power 24 is equal to e. They are 12 in number. What is common in this? A6 is common, A12 is common, A18 is common, A24, that is called identity, is common. So the intersection is consisting of elements A6, A12, A18, A power 24 is equal to identity. It is the cyclic subgroup generated by A power 6 and it is of order 4. It's of order 4. So that is what you can do, without using any formula. But I will show you, I have a formula that I can use. It is the cyclic subgroup generated by a power k, where k is the LCM of 3 and 2. What is the LCM of 3 and 2? It is the cyclic subgroup generated by a power 6. You got that also. And this cyclic subgroup generated by a power 6 is a cyclic subgroup of order 4. Correct. Order 4. So what is that you want? Suppose find the number of subgroups of this cyclic subgroup generated by a to the power 21 intersection cyclic subgroup generated by a power 10. So the number of subgroups of this is equal to the number of subgroups of the intersection is the cyclic subgroup generated by a power 6. How many? And what is the order of this cyclic subgroup? That is the number of subgroups of a cyclic group of order 4. It is a cyclic group of order 4. So what is the number of subgroups? That is tau of 4. Tau of 4 is the number is equal to tau of 2 square. That is equal to the power 2 plus 1, 3. Right. So your answer is option 2. So the number of subgroups of the subgroups, cyclic subgroup generated by a power 21 intersection, the cyclic subgroup generated by a power 10 is 3. That is the answer. And that is the detailed discussion of the properties of the several properties of the almost all properties of the cyclic groups. And one question that has come in TS set, Telangana State Set Examination 2019, and 3 questions, example 1, 2, 3 that we have created for you, which can appear sometime later, because these are very good questions that we have constructed for you. And for the construction of these questions, example 1, 2, 3, my student, at a CVR college, Sripath Venkatesh has assisted me. So he has given me some inputs for these example 1, 2, 3 that I have used. I acknowledge his help. So that is the detailed discussion of the properties of cyclic groups and 4 examples that I have discussed in this video. I am sure that you have understood all the properties of the cyclic groups and the 4 examples that I have discussed here. And you know that I have been doing the YouTube videos for JEE main aspirants and TS set, AP set aspirants and CSIR net examination aspirants. If you like my videos, please like, share and subscribe. I wish you all the best. Thank you.